Okay, here we can look. This is the Raman microscope. Some basic introduction about Raman microscopy. As the name says, it is a dual instrument. It's both a microscope, an optical microscope, you can see here. The optical microscope combined with a Raman spectrometer. A Raman spectrometer gives you chemical information, similar to FDIR and things like that. So this is like the brother of IR technology. So they give like complementary chemical information. So it's an optical method. You illuminate the sample with a laser beam, and then you get the characteristic Raman scattering that is picked up by the spectrometer. And that spectra you can acquire chemical data from. So that is the idea. So the fancy thing, the drawback with a Raman microscope is that spectrometer-wise, this spectrometer is a little bit more simplified compared to a dedicated Raman spectrometer that doesn't have the microscope. But the advantage in this case is that you get the Raman signal as a function of the position of the sample. So that means you can map your sample similar to like you do in EDS in a scanning electron microscopy. So you can get where on the sample do I have a certain chemical signal. That's the fancy thing with a Raman microscope. Since it is an optical method, the information the volume you acquired information from in your sample is similar to the size of the laser spot, which is about 1 micrometer in this case. You can use different types of lasers. This machine is outfitted with a green laser. A green laser is usually something you want if you're working with non-organic materials and things like that. And if you're working with, if you're going for more organic stuff and so on, then you probably would like to have a red laser or even up to IR. And why do we want to play around with different laser wavelengths? There's one fundamental thing, and that is the Raman intensity. The Raman intensity, by default is a very, very weak signal. So you want to boost it as much as possible to get a good signal to noise ratio. And it is highly dependent on the wavelength. So if you go to shorter wavelengths, the intensity of the signal goes up a lot. But if you go to lower wavelengths, you also pay by sacrificing a lot of intensity. So why would you like, as I say, in the organic case, you want to have like red or even IR and so on? The reason for that is because the enemy in Raman spectroscopy is fluorescence. So if your laser signal can create fluorescence in your sample, that will, bloat out the whole spectra for you, and you can't see the Raman signal anymore. So then the method fails. So then you want to increase the wavelength. That basically means you decrease the energy of the photons, so you cannot really, accomplish that fluorescence phenomenon. So that is the reason why you want to go up in wavelength. But this machine only has a green laser wavelength. This particular brand, Horiba xplora Plus, can be outfitted with 3 lasers, but we only have 1 at the moment on this one. And since it's an optical microscope, most people understand everything about the optical microscope, so you can put the objective glass slides here with your samples. You can have transparent samples. You can shine through them if you want to have the optical imaging can be a transmission. The Raman scattering is always something that scatters up back to the spectrometer. You can have, of course, completely solid samples also, and have illumination from top on this machine, no problem with that also. What's more to say about this? As I said, it's important to boost the signal. So you have different objectives, different magnifications, but normally the distance from the objective to the surface depends on the magnification of the objective. That's very rough to say that, but in general you can say that. So by taking a more high power objective, you come closer with the lens to the surface, which means that the space angle it covers becomes larger, and you can pick up more of that sort of sacred Raman intensity. So that's why you want to have a big objective as close as possible. On the other hand, if your sample is very rough, or I mean, you can even run liquid samples if you have an objective glass that is shaped to contain the liquid, so you can even measure Raman signals in liquid. But then you don't want to dip the objective, so in that case you want to have a smaller objective to be able to keep a little bit distance to avoid that kind of failure, and then you sacrifice intensity again. The microscope is what is called a confocal microscope. What that means is that the information comes from the focusing point. So when the laser shines to the sample, it doesn't reflect the Raman intensity from, what shall I say, all the part that the light is traveling through the sample, but only where the focus is. That is very nice, because then you can make, what shall I say, depth profiles. You can also, if you don't want to do a depth profile, a classic thing is that you want to find out what something behind the glass contains. I mean, for example, Raman spectrometers can be used to sort of verify a medical component inside the glass bottle without opening the glass bottle, right? So that means you put the focus inside the liquid of the bottle. You can build a, you can't fit a bottle in here, but theoretically you could do that with a Raman spectrometer. So that is it's like very versatile, very easy to use. So I mean, it's quite fast to take a measurement with this. So now we're going to go through the basic thing to get this up and running. Step one, I mean, usually everything shall be off here. And it's very important that you do this in the right way to avoid error. And the first thing is to turn on the electronic boxes, these two. And then you need to wait. And you should wait for like about 1 minute at least. And the reason for that is these needs to boot up properly before we start the PC. Otherwise, the USB interface between the machine and the computer is lost. And that will create an error for you. And that error, usually it is signaled as something called a Mauhauser error. There is a separate movie for that also if you end up in that problem. But the main reason why you get this error is because you started this box and then you too fast start the computer. So you need to wait for these to initialize themselves before you can start. So that's step one. So let's start up the PC now. I hope we have waited long enough. I think it will be fine. Since this is a laser equipment, I mean, there is laser safety precautions here. But this is a very user-friendly machine because you see there is micro switches here. And so you need to close the doors, and that will sort of enclose the whole area where the laser is. So there's no risk you expose yourself to the laser beam, because a quite strong laser is 100 milliwatt laser. So you're fully protected. And if you open this, the laser is immediately blocked, cut. So if you open it by accident. But there is something to take notice of here, and that is if you haven't, when I close here now, you can hear this little sound. There's a clicking sound. And there's two micro switches. So when you close, you must make sure it is fully closed. If this is a little bit open, then the switch is not closed, and that means the laser is off. And then you're wondering, why don't I see any signal? And because you haven't closed the box. It's very important to close the box, right? So that is a nice thing to make sure on that. The program is called LabSpec. So this is the login interface, and you can run user account on this machine, but it's such a simple machine, so we all use this admin account. Admin account is the username with the capital A and admin, and the password is the same admin. Some people want to have their own user account, so you can create that here on that user icon there, because you get your own user space and can have your own configurations and so on. So now you start to hear a humming sound. That is the spectrometer that starts initializing itself. And here it says warning. And if I click on this, this little eye here, it says that the xplora electronics has been reset, and that's because it has been off. So this error is okay. But if they were started in the wrong way, then you get other errors here. For example, that Mauhauser error and so on. And what you should wait for here now, a good sign that you are on the right track, is that when the spectrometer has finished, it will calibrate this XY stage. So, and then it will come up here on the screen. Here it says, XY stage control was restarted, now we want to calibrate it. And when we click OK here, it will start to do that. And before you do that, you need to check that the objectives here has some free space here, so you don't crash into the objectives. So when I click OK here, it will start to move around, to calibrate it. And when if the machine do this and finish this, then you know that the electronics connection to the computer is all working fine. If you don't see these messages, or if this jams or something, then there is a connection error. So now everything is fine. The next part is to do the calibration of the spectrometer. But before that, we would like to, well, if I say like that, there's not so necessary to calibrate it. I mean, the deviation between calibration is very slim on this machine, so usually there is not a calibration issue. But by doing the calibration, you get a good test that all things is working. So step one is to actually see if we can get some laser signal going. So to get the laser going, we need to close the enclosure. And before we close everything, we can put in the calibration sample and make everything ready here first. The calibration sample is just a silicon chip, a wafer, cut out silicon wafer. I position it here in the microscope. And then you see we have red, we have yellow, and we have white. I mean, if you don't know something about light microscopy, you know that these are color-coded for their objective, magnification that they have. So we start with the smallest one. And then I click on the camera symbol here. It takes some time, and then the image change. And then one can change what type of objective I have. So here it says 100. I can change to 5, which is the red one. That is just to make the scale correct here. And then I can change the intensity of the light on the machine. So I need to drop this so you see it was too bright, right? If I want to move around the stage, I can use the joystick. And this joystick is analog, so that means if I move a little bit, it moves very slow on screen. If I move a lot, it moves fast. So it's not like a digital on and off. So you have very good control here. And if you want to change the height of the stage, that is what you do when you're focusing in a light microscope. Then you rotate the joystick. So now we want to see some. It's nice if there is some dirt on the silicon wafer, because if it's completely clean, it's very hard to make good focus. So if there is some dirt, it's very nice. You can position some of these dots in the center here, and then I can, if I turn the joystick, I can see now they become blurred. And now they can become like sharp, right? So that is step one. Get it into focus on the smallest objective. And then we rotate up one step, take the 10th time objective. You see it changes, it becomes blurred because they are not really good at focusing. I mean, there is a little bit offset. You can change this if you want to keep the scale. The nice thing is that it also keeps the intensity program to each objective. So instead of fiddling with the light all the time, if you do this once, then it will be correct. So I want to have an even gray. And when you rotate up like that to higher and higher magnification, 99% of the time to reach correct focus is counterclockwise on the joystick. I say that because it's easy to get lost in the focus. So if I try to move counterclockwise, and I just turn very little, you don't want to go fast here. I look on the screen, and you see it comes into focus there. Now I see the dots again. And then we go to the highest. So if you don't go higher and higher objectives, it's very hard to start directly at 100 times magnification. Now I change here to 100 objective. It's a roughly okay gray. Still counterclockwise, take it easy. Yeah, and then we see that I fail. You see it starts becoming dark. That means we're coming out, completely out of focus. So that means I need to try clockwise this time. There we saw something. See some dot there now, and try to translate around here. And there we have some more stuff to see. It's easy to see if there is bigger dots. So now it is in focus there, right? So now everything is set up to actually start the calibration. To get the laser going, we need to close the box. Make sure it is completely closed. Since this box slams a little bit, it's good to check that it's still in focus so the stage hasn't sort of, by the vibrations changed. But to do the calibration, we need to first turn on the laser also. That's why this box is. There's a key here. You need to turn it on. So many people forget that, and then they sit here for 1 hour wondering why nothing works. Yeah. I can't emphasize this enough, that you need to take it step by step, because if you don't have the laser, it is so easy to get confused on the way. So check your lasers on, check that the box is really closed, and then the next step before the calibration is that we can here it says laser off and it says 100%. So this is the intensity of the laser. I change this to 1%. That's the weakest. And then I turn on the laser here. Now it's laser on. So now the machine has turned on the laser. It should be on if everything is fine. So step one is we can check this in the camera view. And on this machine there is 2 cameras. This one that is called the top camera. That's what we're having here. If I click on acquisition here, I can go to top here. It says camera top. So this camera is filming through the microscope straight down. So this cannot see the laser, because if we use this camera, it turns off the spectrometer and laser. So you can only use either one. But there is also an internal camera here, and that can be on at the same time, so to say. So if I switch to the internal camera here, you will see this change. And then you see the green stuff here. This is actually the laser light hitting the camera. And that's the reason why I put 1%, because if you have 100, it will be all white. So if I turn off the laser now here, you see it's black. So this means, okay, the laser is on, we have the laser all the way through the spectrometer and so on. The next step is to check, do we get the spectrometer online also? Do we see the Raman signal from the silicon? Silicon has a, what shall I say, characteristic Raman signal at, I think it's 520 reciprocal centimeters. So we can go back to the top here if you would like, because this internal camera is weaker than the top camera, so you want to use this top camera. So go back to spectra here. Here's an old spectra. It is actually an old spectra of the silicon. We can see that the peak is, here is 500, 600, so about 520. So we can just discard all old spectras, close all data. Don't want to save anything here, like that. And to run the spectrometer, we have two options. We can scan, what shall I say, make a, just the play button is like, just run the spectrometer over and over and over again, real time, and see what's happening. And the record button is when you actually acquisition a real spectra that you want to save. These color buttons, if you have several lasers, you can pre-program those to do certain configuration and measurements based on the type of laser. But since we only have one laser, we don't use these buttons. We only use the main record button or the play button. And then there is this record button with that kind of matrix, and that is when you do these kind of mappings. So a mapping is when you want to get Raman spectra as a function of x and y position. You can take like 10 by 10 points, or so many points you want. And you can also do a depth profile and make a three-dimensional volume also if you want to that. So you can measure both depth as a function of depth, as a function of x and y. Then you get that kind of 3D matrix. But in this calibration phase, the step one is just to see, do the spectrometer work before we start the calibration. So if I click here where it says 1800, I see I have four gratings of the spectrometer: 600, 1200, 1800, 2400. The higher grating you have, the higher resolution you have wavelength-wise in the spectra. But how big range, I mean the lowest wavelength and the highest wavelength you can see in the spectra becomes narrower also. So this is a very classic spectrometer problem. Either you want to see the bird's eye view, the whole spectra, but then the resolution of the peaks become worse. Or you want to see just a single peak, and then you can resolve that in more detail by increasing the number on the grating. So now it says 1800, so I think 1800 is fine. You can use, for this just initial check, you can use whatever grating you like. It is on 1800, so we just leave it on there for convenience factor. And then we can see that the spectrometer at the moment, the center of the spectrometer is on 883 reciprocal centimeter. And the silicon peak is on 520. And the range it covers now is 100 to 1500. So that means even if the spectrometer, the center of the grating is on 800, we still, 500 is within 100 and 1500. So we don't have to do anything here. Otherwise, if we really want to change, we can put this on 520. If I write 520, then the spectrometer grating will start to turn. This takes some time. And then it will position itself at 520. So now the silicon peak will be exactly on the middle. If I click the play button now, it will start illuminating the sample and do, what shall I say, a continuous measurement. And then we see something, it's just some noise down here, because the intensity is still 1%. So let's just put the intensity to 100%. There you see a small peak now coming up. So, I mean, I can if I click here, I can change the scale here if I want. So now we see these 600 counts right at the moment at that 510. So this is a signal from the silicon. So, and how many counts you get depends on how long acquisition time you have on the spectrometer. And with the play button, it says RTD is the play button. So it says half a second now. So the idea with the play button is get like a real-time update here. You don't want to wait like minutes, you want to see in seconds. So if it's noise, that doesn't matter. This is just a check. So this means everything works now. Laser is obviously on. We get a Raman signal from the typical silicon and everything. So what we can do now is to calibrate. And I don't want to waste so much time on this. So if I click here on calibrate, you see it's red. Then I can choose, do I want to calibrate all lasers and all gratings? I recommend you do it. We only have one laser, but it will do all the gratings. And then it checks all gratings. But to save time, we just do the one that we have. So I choose current laser and grating. And then it says, make sure everything is turned on and so on. And we have all of this, everything on there. So just let it run the calibration there. So what the calibration actually doing is it measures that silicon peak a little bit more accurate now, and then it checks, is it exactly at 520 that we expect? If it pops up at 540, then it will calibrate and adjust the spectrometer so it will be at 520. And it says pause here. That means it was fine, nothing wrong. So, I mean, you see there's like two curves here. One is the data and one is the sort of the modeled peak. And then it checks 520, so it's like, that's okay. And it says finished, and then this becomes green. So that means now it is calibrated, we can work for this for the rest of the day. The calibration is valid. So everything is fine here. So then if we don't want to keep this, and then we can just discard all that data. So now we have come, what shall I say, to a position where we actually can start operating our sample. So the next step is we can replace the calibration sample to something that we want to test. So let's try that. So to remove, I rotate the object away so I can easily pick this out. I take out this. We can just, for the day, we can run the, what shall I say, the demo samples that I have here also. Yeah. Let's try. I think there's two demo samples here. I think this is some kind of plastic, I don't remember what. And then this I think is, I think it's like acetyl salicylsyra, painkillers. So we can try that, just to get some kind of signal. We start with the red one. We can go click on camera to see the camera view. So usually you want to have this open in the beginning and see here what you see. So there we see this is the edge of the glass slider. So I want to move the stage over to that. Here it comes, right? This is the powder, and you see it's completely out of focus. So we need to fix that. And you see, if I hold it, it goes very, very slowly. If it's very far off, like in this case, there is a small little wheel here. You can just pull on the wheel instead. When you come into position here. So here we can see these crystals with the medicine. So then we just repeat the same thing here. You can go up, make sure it is in focus. And since the powder is big, you see not everything can be in focus at the same time. If you want to have it in the focus at the same time, there is something called this view sharp function here. You can, if you want to use that, you click here, and then it changes the focus and takes several images and what shall I say, recomposition the picture so you can have everything in focus. This is very big, so I think we need to increase a lot. Let's try this, 50 perhaps. But this is, I mean, mostly like a practical thing if you want to have an image of your sample. When you're working with the microscope, it's not so important. But if you want to take measurements and you want to produce an image in your report, then it can be good to have one image that shows everything in good focus. So now we can see major part of the crystal in focus. Without that function, you see it's much more blurred. You can only have one part there. I rotate in the 100 objective. Let's increase the light a little bit. And we try counterclockwise. Here you see it comes. It's in focus there now, right? So the laser, I mean, that green little dot is about 1 micrometer actually in size. So that dot is sort of quite representative of the laser beam spot size. So that is where the area of information will come from. Theoretically, if the material like a crystal like this is transparent, or laser can bounce around and things like that and scatter, and you can get information from wider areas. But this gives you some kind of feeling. One thing to take notice of is that the program assumes that the laser hits in that center. Doesn't have to be like that, because this camera can be misaligned. So if you want to actually check that, then you put in a small little tissue paper, close everything up, turn on the laser 100% for some time, turn off, check in the camera, because then the laser will have burned a hole in your tissue. If the hole is up here, then you need to realign it on the screws here. But if people don't fiddle with this, then it should be calibrated like that. So let's close this up now, because we want to run a spectra on that thing. Now you see it became a little bit offset due to that, so I can refocus like that. We can go here to the acquisition tab. So since we don't know what this, what shall I say, sample contains really, I mean, as I said, I think it's this acetylic acid. But let's make like a general scan. We want to have a wide scan, so let's scan the full range of this 1800 grating. I think it reaches 1500. So here it's, if there's a blue mark here, you see you can click and make it blue. Blue means that you want that function. So if I click here, then it will scan from 100 to 1500. And then I can see, here it says acquisition time, so there's 2 times. RTD time was for that real-time signal. Acquisition time is for when we actually want to acquire a real spectra. And that we usually don't want that to be half a second and so on. But to get some estimate, how long should I scan? Well, one way to do is we can check on the play button and just see how strong is the signal. Now we can see something there, right? So at 100% laser, at half a second, we get this one at 0. What's that? That is that, what shall I say, we can say the reflected laser. That is not part of the Raman signal. This is the interesting area, right? So here we can see the spectra that's of interest. And you see it's like 450 counts at half a second time. And we can run it up to 65,000 counts. So, I mean, at least we can boost this 10 times at least. 5 seconds will give you 4,500 counts. 100 seconds will give you 45,000 counts. So about 1 or 2 minutes will be nice on this particular sample. So let's try that. Let's run it for 60 seconds. And then we just acquire. But before we do the acquiring, we can go down in a table and look on other options that can be important to talk about. One thing to talk about can be the thing called the spike filter. The spike filter is that sometimes when you scan, you can get a peak that is basically 1 pixel wide and super high. That is caused by cosmic radiation hitting the camera here. So that is just noise, and you want to remove those things. So you can remove them manually, or you can use this filter and choose to make multiple accumulation, and then it automatically compares two spectra that it takes in a row and removes. So that can be good to know something about that. The other important part are these two in the end. It says slit and it says hole. And these are apertures. And this, you can choose 500, 100, and 200, and it's the same here. No, it's 100, 300, and 500. So if we talk about the slit aperture is the aperture to the spectrometer. That controls, what shall I say, the wavelength resolution on the spectrometer. If you choose a smaller slit, intensity will be lower, but resolution will be improved. What shall I say, for most users, you can just leave it on 100, that will be fine. That is like default, works in most cases. But the hole is important. The hole is that confocal aperture. If you have it on 100, that means you get the information from where the focus is. If you increase it to 500, that means you basically remove the confocal feature of the microscope, and then the signal comes from all paths the beam actually hits. And sometimes you want that, because if there's the same material everywhere, then you don't want to remove signal by taking signal from just the focus point. You can just take everything then. So the only reason you want to have it from the focusing point is when you want, if you have material you want to study by depth. The concentration is changing or something like that. Then you want it to be on 100. So this is an important decision to make. You can just leave it on 100 for now. Since this is just a medical powder, putting it on 500 will be actually more advisable here. That's it, we just leave everything there. Click scan. And now it scans, and we wanted to scan for 1 minute. So you see this little green bar start coming up here. So we just have to wait for 1 minute. And now we're using 100% laser. There can be a risk of using 100% laser because it can damage your sample. As I said, it burns hole in a tissue paper. If your sample is sensitive, it can damage it. And if you have that, you will see that you have in the camera, you will see a hole after a while, or it becomes black or stained or something like that. But you can also see it in the spectra, because the spectra is changing over time. I mean, the material you're looking on is decreasing intensity, and then something else is starting to appear because you're creating soot or something like that. All right, now it's scanned for 1 minute. Let's rescale everything. Here we see the spectra from 100 to 1500, because we wanted to scan from that range. This you can continue here in the tab and go to analysis, for example. You can open the peak tab. And here you can choose to identify peaks and so on, where they are and so on. You can also click on this wizard boy here, and then it will see. There should be a free part included in it. Yes, so here it puts the data. You can look on this more in detail, but I don't want to talk too much. You see it makes some item identification, one compound, so it says aspirin, which is this acetylsalicylic acid. So if you have run chemical analysis, FDI, I mean, you know this. It's very straightforward. Nothing new under the sun there. If you want to, if there's too many peaks identified and so on, you can change the play around with the parameters here, but I will not say more on that. It can be worth mentioning if you go back to acquisition tab. As I said, this 1800 grating has a smaller view field in wavelength range. right? So if I want to scan longer, I want to have more than 1500, I want to scan up to 3000. Let's say I do that. I write 3000 here. And then we can, let's say we want to save a little bit of time also, so I put it down to 30 seconds. And then we scan. What will happen now is that the machine will scan as long as it can, and then it will reposition that grating in the spectrometer and then continue the scan. So it will be 2 consecutive scans that will be merged together. That is very nice, because then you have the resolution of the grating and you have a broader view field. The drawback is that for each, what shall I say, scan sections it does, it adds some new scan time, right? Because if you have a very high grating here, then it will be like 5 sections or something, and then it will take 5 times longer also. So here we can see the first part of the spectrum now, and now it's doing the second part now. So then we'll see the continuation there. Yeah. So here we have the second part now. And if, as I said initially here, I said that the enemy of Raman is fluorescence. If this was a fluorescence problem case, we don't have it, we see a good signal here. But if it was a fluorescence, then the signal will start low here, and then as longer the time it takes to scan, I mean, the machine always scans from the low wavelength to high wavelength, reciprocal. Then the intensity will be low, and then it will go higher and higher and higher, like a curve like this. And that is because fluorescence is a time-dependent function. The longer the laser illuminates, the more and more fluorescence you get. And that means the signals will still be the same, but that background will, so you see some peaks here, and then everything will just come under that baseline. So that's why you cannot use it if there's fluorescence. So there's 2 ways around that. Either you switch laser wavelength, and we can't do that on this machine, or you need to decrease scan time. But if I want to scan for a long time because I want to have the statistics, how do I do it? So this is very similar to the charging problem in the scanning electron microscope. So what you can do, you can scan for shorter time, but you can take multiple spectra. So you scan for 1 second, 1 second, 1 second, and then in between you make a pause to let the fluorescence settle. So then, now we wanted to take spectra for 1 minute. So instead of taking 1 spectra for 60 seconds, we can take 60 spectra for 1 second, right? Or actually, perhaps we want to take 60 spectra 1 second each, but 1 second pause between each also. That can suppress the fluorescence, but usually fluorescence can be a very, very brute on you, and it's very, very tricky to get a good signal from that. When you have reached this, there is more, you can process the data, you can subtract background, baseline correction and all these kind of things. You can play with that yourself, I won't say more on that. What I can say is that what most people do is when they save the data, you have 2 options. The LabSpec 6 is if you save it in that, then you can reload it in this program. I always do that if I want to go back and do some changes here, but I also save it as text files because text is CSV data, you comma-separated value, so then I can import it in other plotting software and things for publications. So that's what I always do. So the last part to say something about here is this mapping function. The strength of this machine to correlate the lateral position versus the signal of the spectra we have here. So if I go back on the camera view, this is what we are seeing here on that small little crystal grain. Let's change the magnification on the machine so we can see like a whole grain or something. So let's go down in the magnification here. You can try this. Now we will pay in intensity since we did that, but now I can see like a whole grain here. if I put this right scale here also, it's a 10 times objective, we can see that the grain, it's about 0.5 millimeter wide, those grains. So we can check this intensity again. How big is the intensity? We can remove these old spectra. And we just click the play button to get the signal. Now we see the spectrometers shows, if I 2,700 to about 4,000. That is because the last time it needed to move the grating, and when it's finished, the grating stays where it was. There is some signal here around 2,000. If we don't want to see that, I mean, then we need to reposition the grating, but we can work on this signal, for example, just for the demonstration. So let's say that this is fine. You have about 400 counts still on this part of the spectrum. I guess that's also a similar intensity. Wasn't so big change between these objectives really right now, at least. So let's go back to the camera. So let's say we want to do a X and Y mapping or a line scan, for example. I can take the line tool here. It's already selected here. So there's a tiny line here. So where I position this line is where I want to take the data points, right? So let's say we want to take the data points not horizontally, perhaps. If you want it diagonal, you can choose such a tool as well. I mean, if you want to scan in another direction. But yeah, you can just keep it like that. Take this straight on like that. And let's make it so it goes over that hole there also. And then you see a lot of points, what shall I say, marks here. So if I go down here, it says map, and here there is, you can see the positions. So it's 400 points now in the X direction. That's a lot of points. If we want to scan for 1 minute, that's 400 times 1 minute. So here you can see it becomes very important to have fast spectra acquisitions if you do mapping. Otherwise it takes forever. But we had a somewhat good signal. I mean, 450 counts. That's a very low count number, but that was half second. But for the demonstration, we can run it for like 1 second. Then. Let's say that. Then we get almost 1,000. So let's say the acquisition time is 1 second. And we don't need to do 400 points. Let's say we just want to do 20 points. Then we can see total data points is 60, and then it will take 3 minutes to do that. And that is because it wants to scan from 100 to 300. We don't want to do that. We can just let the spectrometer be at its position. We don't want to, because moving the spectrometer takes time. It takes like 1 minute to just move it. So better to keep the spectrometer at a fixed position. Now we see it takes 1 minute instead. Go much faster. So let's do that scan straight on there. And here it says Z also. We don't want to do the Z. We just want to do X scan there. We click on this new record button with that matrix thing there. So what the machine will do now, it will start on the left, take a spectra, go 1 point, take a spectra, so then we get the signals as a function of that lateral position. We can rescale here. Here we see our signals, and here it gives a intensity as a function of X. But then, okay, what intensity is this? Well, it says green here, so we have 3 cursors. The red, the green, and the blue. So if I take this one, Here, the second one was the red, apparently. Analysis. Here we can see that we can reset these positions. So let's put the green one on this. It's from 2,900 to 3,000, perhaps. Now you see the green marks that peak. And then we can put the blue one on this other one, and what's that? It's like 3,050 to 3,150, something like that. And the red one we don't want to use. So now the green is the height of the peak. That's the count here. We can change it if we want something else. We can choose the area of the peak as well also, and this is the area. So now so this is just the spectra from one point. But here we get the intensity or the area of that peak, that green peak as we call it now, as a function of x position of the sample. And it varies a little bit. And since you remember we scanned over that hole, there is very little signal to the left here, and then the signal goes up. So why the signal varies in this particular sample is due to the geometry of the surface. So sometimes we are outside the grain and sometimes on the grain. But I mean, it's the same thing. Is this a change in concentration in the sample and you don't have those geometrical surface effects, then you can see the change in concentration here as a function of distance, right? And what you usually want to do is you want to compare. I mean, this is the green one, so I can change this. You see now it says green G divided by B. So this intensity is the ratio between these two peaks now. And that's very interesting because usually the intensity changes by geometry or other artifacts. So, and then how can you distinguish if it is a change in composition in the sample or an artifact or an issue from the surface the surface roughness and so on. So by looking on the intensities in the same spectra, if one peak goes down and one peak increases, that is a strong indicator that this is actually some real thing happening inside the material. So the change in these peaks, this one shrinks and this one rises, that ratio is what we see here now. So here we see a change in ratio and here there's a smaller ratio difference. So that is usually you want to play with. So instead of doing a lateral scan, if I go back to the camera here, instead of having a line like this, if I go down here, where it says map here, now it do, in the x direction it do 20 points, but I can turn off that and turn on the z direction instead. That is the depth. And since if I have the hole on 100, it will be focus sensitive, right? That's what you want to do. You want to pick the spectra from the focusing point. So if I do that instead, and then I choose 0 is where the focus is, and minus is that we want to go down into the sample, right? So now it's minus 50 microns into the material. And we can make 20 points. We can take even 100 here, let's say. So now it's 5 micrometer steps. It goes into the material after. So instead of scanning across the surface, we're scanning through the material now. And this crystal is a little bit transparent, so it's plausible to do this. So let's do that. And it uses the first point there. So now we're scanning as a function of depth instead. Intensity as a function of depth. And now it says blue map now, you see. So now we get that peak, the area of that peak that was we chose before, as a function of depth. And then we can see that first it was very low signal and then the signal is increasing. And that makes perfect sense because if if you are a little bit out of focus first, then you are grabbing signal from the air, not the particles. So that's why most of the laser beam is completely out of focus at 0.0. And then we start coming into the material, and then it's like half the laser is inside the material. That's why we get that improvement. And then after a while, the whole laser is in, we get the whole volume of collecting signal, and then it of course increases. So, and this is what we can expect for a sample that is 100% the same chemical all the way through, and so on. So, I will say this is quick guide on how to use the Raman microscope. And I showed the sort of the strengths of this. I mean, instead of doing a one-dimensional scans like that, you can make an area if you want also, or that volume. You can scan X, Y, and Z. But since if you're scanning 10 dots, 10 points X, 10 points Y, 10 points deep, that's 10 by 10 is 100 times 10, that's 1,000 points. It gets a lot of points. And if each spectra is a few seconds, then you're talking hours. So it's not really realistic to scan like high resolution, 3-dimensional volumes if you don't optimize the spectra so you can take them really, really fast. And to take spectra really, really fast, you need a sample that gives you a strong signal. But if you don't have a sample that gives you a very strong signal and you need to scan for a long time, then you are like sitting duck here. You can't really come so much further on that. But that's the basic thing. And shutdown is like nothing strange. Pick out your sample, turn off laser, close program, close PC, close the electronic switches. That's it.